Hello and welcome student to the first lecture of the course MA412 Linear Algebra. Okay, this is lecture number 1. Okay, linear algebra is the subject where we learn about linear space and linear maps, their properties. Okay, so how this idea of linear space and the thing came. So let me talk about a little bit idea first. So this idea was actually originated from the physical vectors. So in real life, you know that physical vectors. So for example, these lines in Euclidean plane. Okay, so you can talk about these directed lines from the origin. Okay, 0, and we call it vector, right? It can be true in 3 dimension also. If you have 3 dimension, and then you can talk about vectors. So you have 3 components. Okay, 3 components like that. Okay, so this idea of physical vectors was there before the idea of this mathematical vectors. So what mathematician did? Mathematician actually analyzed this idea of physical vectors, and they defined this in more general way. Okay, so how to define it? So let us start with the definition. So we call it vector space. Or linear space, both are same. Okay, so what do we need? So we need another set V, another set is called the field. So let me define by this notation F, maybe this bold notation, and we need 2 maps. Okay, one is plus and one is dot. So this is my ordered quadruple. Okay, and what are those maps? So the maps are, so this addition, say map from V cross V to V. Okay, and we call it is addition of vector space, and then you have dot, and this is a map from F, the field F cross V to V. Okay, so these 2 are the maps, and these maps should satisfy few properties. So what are the properties to satisfy? So properties 1. So with respect to that map plus, this is an abelian group. Okay, so I'm assuming that the basic idea of group theory, field theory, I've already learned in your undergraduate course. So abelian group means what? So that means it satisfies few conditions, right? It satisfies associativity, existence of identity, other things. So here you can say, so this is called 0 element. Okay, the identity is called the 0 element, or we will see that this is called, actually we will define these elements of this space, this set V as a vectors. Okay, so abelian group, similarly the dot and this product, there should be some relation. So what are the relation? You can say that something called distributive relation. So what does that mean? That means, so if we choose okay, so one more thing, say abelian mean commutative. So we have learned this thing, right, already, and there will be few such properties. For example, one is the identity of the field. You know, field also identity. For that, and for every vector v, it is v. This is for all v belongs to capital V. Okay. Similarly, the other properties, for example, the distributive property of dot over the addition. So you choose a scalar c and then choose vector v1 and v2, and if you just take addition and then do multiplication, scalar multiplication, it is same as first do scalar multiplication, okay, and then do addition. So this two doesn't matter. Similarly, it is true from both sides. Both sides means you can have like these some two keys, and this is obviously true for all C belongs to the field F, and for all V1 V2 belongs to that non-empty set V. Similarly, if you choose arbitrary, I mean for any such constant, they also satisfy the conditions C1 dot V plus C2 dot V. Okay, this is all. This is for all. Always, whatever I am writing, these are for all. C1 C2 belongs to F, and for all V belongs to V. Okay. And same thing is true for so this is addition of field. This is the addition of field, and this is addition of the vector space. What I am saying. Okay. So do not think that both are same. Yeah. So some cases both can be same, but in general they may not be same. For example, addition inside the vector space may be completely different in addition of that regular field. Okay, do not think that both are same operation. Okay, they can be same for certain cases. And now if you multiply say two elements C1 C2, and then you do the scalar multiplication. So this is the multiplication of field this side, and then you do the scalar multiplication. It is same as if you first do this multiplication, scalar multiplication, then this will be, so this is, remember this is a map from F cross V to V. So once you do scalar multiplication, then C to V will be element of V, and then you do scalar multiplication C. So they are also same, and obviously addition is that because this is a group with this addition, abelian group, so that zero element is also satisfy the property that if we add zero element to every element, that will be same element, right? So for example, this I am not writing, but this is it is there inside this property that for V plus 0 equal to V, and that is equal to 0 plus V, and that is true for all V belongs to V. Okay. So these properties are generalization of the property which we already have find out in physical vectors, that if you add two vectors, again it will become a vector. If you multiply by another scalar, means if you just make it the direction, keeping the direction same, you are just multiplying the length, so the vector becomes longer but the same direction, right? So those are the properties which are generalization of the physical vector properties, and if your set V satisfy these properties, then we call V is a linear space or vector space, whatever you want, linear space over if this is very important, the field is very important, the underlying field. Okay, and so elements of V are called vectors, and elements of F are called scalars. So these elements are called vectors and other elements called scalars. Okay. So so let me use. Okay. So these are basic properties of. This is the way you define a vector space. And now um, let me give some examples. So examples. So one was if you choose any fields and any copy of the fields. For example, you just take R, which is field of real numbers, and then you choose a vector space V, some say n copy of R. You can choose any field here. Okay, so I'm just giving an example, and then you see that this V informs a vector space over R. So this is the symbol. We say that V is a linear space or vector space, whatever you feel like, linear space over R. Okay, and so elements of these Rn you can write down n tuples. So there are two ways to write down these things. Some people write down these kind of column vectors like A1, A2, and An, such that Ai's are elements of real numbers. Some people write down in the column vector space, right? This is the row vector. Some people use column vectors also, like other way. Okay. So whatever you feel, you write down, and then here you see that obviously the two maps are obvious, because if we choose two elements, say A, the vector A, so let me write down this symbol A, which is that n tuples, and B is another n tuples, say B1 to Bn, and you can add those things, and what will be the addition? Addition will be the component wise, A1 plus B1 A2 plus B2, and similarly An plus Bn. Okay, and the scalar multiplication will be also obvious, because if you multiply a constant C to that vector A, which is A1, A2, and so on, and An, then the result will be CA1. So for the sake of things, I am not writing C1 A1, C1 dot A1 C2. The C1 A1 means C1 dot A1, and this is the scalar multiplication. So this is that the meaning we are assuming, right? Otherwise, every time we need to write down C1 dot A1, C2 dot A2, C2 dot A, right? C1 dot C1 dot A1, C1 dot A2, C1 dot A3, and C1 dot A. Instead of saying all those things, we are just writing CA1, CA2, CA3, CA3. Okay, and then you check all the other properties they satisfy. So these two operations satisfy all the other properties of vector spaces, right? So this is canonical things, canonical way of defining these vectors. Okay, and now next is we can talk about space of matrices. So what is that? So example 2, this space of matrices. What is this? So you take any matrix over any field. So let me write down this symbol M. Okay, so you can take M cross M matrices, doesn't matter, or M cross N, whatever you feel, you can write down that. So let me take in general that M over some field F, and this field also you can choose anything. So this is what, this is a collection of this matrices, right? Like A11. So in many rows are there, in many columns are there. So A1n. Similarly, A1 and Amen, right? This kind of matrices. And these Aij's are entries which are element of the field F. Okay. So here what you do, you addition this, which is we already know, the addition of two matrices. Okay, so how do you define? So you have the first matrix, you can write down Aij, right? And second matrix you can write down Bij, so that are ith rows and jth columns entries. And when you add those things, it will be having Aij plus Bij. So this will be the ith row and jth column of the new matrix. So it will be defined by A plus B. Okay. Similarly, scalar multiplication is also very simple. So you multiply by A, so that is C times Aij, and nothing but you can write down C Aij. So you will just multiply by each component. Okay, C by each component. Okay. So again, you check that with respect to this addition and scalar multiplication, it forms a vector space or linear space over the field F. Okay. Now these are very simple observations, and there are many other examples. You can choose space of linear maps, space of. I mean, there are many ways you can do it. So maybe I can give some more example. So for example, you define V is collection from some set to some set. So so you know, no matter which set you are choosing, you can choose some non-empty set is, and you choose function from that set to a field, say whatever the field you choose. You collect all the functions from a set, random set, to a field F, and then you see that with respect to two operations. So what are the operations? You define the operations like the usual addition of functions. So if you have two functions f and g, then you find maybe x equal to f of x plus g of x. That is true for all x belongs to the set S. Okay, and similarly define the multiplication also. So you have a function, you multiply by constant, and this will be again a function, and that will be defined by c times f of x. Okay, and you see that this will form another space. We call this space of functions. Space of functions. Okay, so here it can be any space. So no matter what S you choose, you can choose S equal to F itself. You can choose S equal to F power n, and in some cases it is a special meaning. So we will learn that what are those spaces. Okay, in future. So then again you can talk about other spaces, for example space of polynomials. Okay, so what was the example number 4? So space of polynomials. Okay, so over some field. Okay, so let me first define what we mean by polynomial. So let me define by this symbol P of f. F is a field, and this is what? This is collection of all polynomials. So this is collection of all polynomials whose coefficients are from f. Okay, with coefficients in F. So typical element will be of the form. So you use some polynomial P of X will be of the form something like that. A0 constant term, then A1x, and some highest something say n x power n. Okay, so this n is called the degree of the polynomial. It's called the degree of p, the polynomial px. Okay, and this n is called the leading coefficient. The leading terms has the coefficient is called leading coefficient. This is always not zero, and this is constant term. This is a constant term. So the leading coefficient, leading coefficient. Okay. So you can write down these polynomials of this form: summation ai x power I equal to say 0 to some n. Okay, and then how do you add and multiply? So there might be two cases. So you choose polynomial, another polynomial, say p dash or other something. So let me not write p dash, something p1 of x, and that is probably some bi x power I, but this I may not be from 0 to n, maybe 0 to some m, or maybe some not only even 0, some constant can be 0 also, whatever. So in that case, what you'll have, you just, so the addition will be what? So addition will be pointwise. So what does that mean? That means you just choose the coefficient to add the coefficient of the same power. Okay, so this will be summation ai plus bi x power I, right? And this I can be from 0 to what is the maximum of n and m. The question is that if n is less than m, then what will be the value of ai other than n, right? So that will be 0. So if there is nothing is there, so that is 0. Okay, for example, if you check say px equal to 5x plus 7x cube, then he has here a0 equal to 0, a1 equal to 5, a2 equal to 0, and a3 equal to 7. And if you go beyond, for example, if you want to find out a4, all are 0, right? So if there are no coefficients, that means that is 0. Okay, so this is the way you can add, and also you can do scalar multiplication. How do you do scalar multiplication? So you have a constant, and then you have the polynomial px, then you multiply c times this ai x power I. Okay, so this is equal to so the polynomial was ai x power I, then you multiply by c. So new coefficient will be cai. Okay, so this will be coefficient. Now with respect to this scalar multiplication, again you see that this forms a and again you can easily check that this forms a again a vector space, a linear space. Okay, satisfy all the other properties. And there are so many ways you can define vector spaces. Maybe some of those examples you can find out in your exercise. Okay. So now maybe let me just give one more example and then I will stop. So what was that example number? 5, 6 space of polynomials, space of sequences, and then I will go to other things. Okay, space of sequences. So again, so what do you mean by sequence? So the sequence is a sequence. So we write down that symbol in. Okay. So this is what these are actually a map from this is a symbol. So let me write them properly. A sequence in some field f is a map. Map means function, okay, from natural number to f. This is the meaning of sequences. And then, so what will be the outcome? So outcomes will be n. So for example, there is one mapping to a1. A1 is element of a, right? So we will write down the symbols. N belongs to natural number, or n greater than equal to 1, whatever you feel good, we can write down that same thing. Okay, so if it is a map from this to this, what does that mean? That means that if you can add two such maps, and adding two such maps is simple. Then how do you add two such maps? So similar way, the way I define functions. So it's kind of, you can see that it's kind of function space also, special kind of, because this will be taking values on the domain will be always on natural numbers, and domain is the function, right? So you can add n plus so the sequence n plus bn will be of this form, n plus bn. Similarly, scalar multiplication, you can write down the product, right? Okay, so these are basic examples. So now let me go to the next things. That is called substructures of this kind of vector spaces, and those are called subspaces. So what do you mean by subspace? So let me define it. Subspaces. So let me just tell you that in algebra you have learned this kind of structure like groups, subgroups, right? Fields, subfields. Similarly, here also you can have the substructures, and so let me define properly. So what do you mean by subspace? So a subset, say W of a vector space, or linear space, whatever you want, no problem. Linear space V over, let me write down this symbol. This means V over the field F. Okay, some field F is called a subspace of V over F. So again, equal subspace of V over F over the same field if something happens. If what? So if W itself is a linear space, with respect to same operation, that addition and scalar multiplication. Okay, with respect to the same addition and scalar multiplication, scalar multiplication. Okay, so if this is possible, then we call it a subspace. Okay, again examples. So let me give you a few examples, then you will have understanding. So remember, in the first one we given that we have V, and then it is R power n, and then we check that this is vector space over R, right? Now here you can choose a special subspace, like for example you can choose the diagonals. So diagonals are what? So you can choose elements of these forms. For example, x. Okay. So these are kind of diagonals elements. Okay. So you check this is a normal set, and this also forms a W is also a linear space. linear space over R. Okay, and that is obvious to check. You can easily check that W is also a linear space. Okay, so the W is called the subspace of the original space V. Okay, and similarly what was our second example? Second example was so let me check it. Matrices. So here also you can choose a specific kind of matrices. So for example, maybe there is only one element in first row. Okay, like that only on the first entry is 0. So A11 is 0. And this will be again a subspace, because if A1 is 0 and if we add two such matrices, again it will be 0. And multiply by a constant, it will be 0, right? So whatever subspace vector space we have done an example, we can have all the subspaces. Okay, similarly let me give for polynomial, you remember the vector space which is space of polynomial. You can also, okay, so let me write down that field of real number. You can choose any field, no problem. So here you can choose a subspace, special kind of polynomial. So what does that mean? That means a polynomial whose the constant term is 0. Constant term is 0 means what? So that means you choose all px belongs to your v such that, what is the constant term? Constant term is p0. So p0 equal to 0. And again you check that this is again vector space over the same thing. Okay, now the question is that do you have a easier way to check which kind of subset becomes a subspace of some vector space? And answer is yes. So this is our theorem. Okay, so you have VF, and this is a vector space. Let me write them properly. A linear space. So by that I mean that space over F. Okay, and you want to check W is a subset which is vector space, subspace or not. Let W is a subset of V, and then W is a subspace of V if and only if, this is the symbol, if and mean if and only. Okay, so this is, so the condition which I am going to write is both the necessary and the sufficient condition. Okay, if and only the following holds, following condition holds. Condition holds. What the condition? First condition is that the original, the 0 vectors, that should be also element of W. Condition 1. Condition 2 is what? This closed under the addition. What does that mean? That means we have the addition map, no, from V cross V to V, right? So if we restrict that map over W, so that will be mapped from restriction of that map over W. So this will be mapped from W cross W, right? But problem is that the image may not be W in general, but if it is inside W, so what does that mean? That means so this means that any V1 plus V2 belongs to W. This is for all V1 and V2 belongs to W. You choose any element, then the addition will be again the element of W. Okay, so this is the meaning of this map. And third map is the same thing from the scalar multiplication. So you choose an element C and from field F and X from W, and this element of W. That is true for all C belongs to the field F and x belongs to the W. Okay. And so what does that mean? That means the scalar multiplication, we are choosing the map from f cross v to v. So you are restricting map from f cross W to W. So the image has to be inside W. If satisfy all the three properties, then we call then it will be a vector space, and vice versa. Okay. So this is final loop condition. Under this condition, one can prove that this should be a subspace. Okay. So let me give a proof, proper proof that is important for this kind of theoretical courses. So one part is obvious, right? If V is a subspace, so if W is a subspace of V, okay, then what does that mean? That means then W itself is a vector space, right? Then W itself is a vector space or linear space, whatever, over F, and hence you check all these three properties, hence all the three conditions are true. I mean, it is obvious that, right? Because W vector space, we had two elements equal to A vectors, right? Now you have to prove the converse part. So what is the converse part? Converse part is okay. So I think one minute here. And condition. No. I think the zero thing you need to prove that the zero is the same as zero. Okay. So condition 2 and condition 3 are true, right? Condition 1 was 0, so that you need to prove. Okay, so how to prove that condition 1? So let me prove that. Let you have a 0 vector, so maybe a 0 dash. So this is your 0 vectors of W, 0 vector of W. You need to check. You need to show that this is actually the original 0 of V, right? Now, if it is 0 vector of W means what? That means for all V belongs to W, that V plus 0 vector will be V, right? So this is true for every element. But again, we know that V is element of V, so V is also equal to V plus the original 0 of the V. So what does that mean? That means the V plus 0 vectors equal to V, 0 dash equal to V plus 0, and now you just add minus V both sides, and that will gives you the 0 vector is 0, and 0 dash equal to the original 0 vector. Okay, so this is the proof actually. Other two conditions are true, obviously. So now converse part we need to prove. Conversely, so converse part means what? So suppose we have three conditions, 1, 2, 3 holes, and we need to prove that W is a subspace of V. That means W itself is a vector space. Okay. So what does that mean? So 0 vector is already there. So conversely, let W satisfies all the three conditions, right? So we need to check that W is a vector space with respect to the same operation, but 0 is already there, so you don't have to prove. What I need to prove? We need to prove that W is a for example, we need to prove that W is a satisfy all the properties of vector space, and that is obvious again because so the to show something abelian group, what extra you need? You require something called inverses, right? So your inverses are nothing but the negative element. So that how do find out that whenever you have a vector v, then v minus also there, and v minus is there because v minus is nothing but so suppose v belongs to w, and then what is v minus? V minus is nothing but minus 1 times v, okay, sorry, minus 1 times v, negative of vector is nothing but minus 1 times the vector v, and minus was the element of the field, scalar field. So this is again element of w, right? Because whenever v belongs to w, then any constant multiplier will be again the element of w. That is a condition 3. Where is this condition 3, right? So if we apply condition 3, so this is using third condition, right? Third property, whatever you say. Okay, so this is the property we require to prove something abelian groups. And abelian property is also same. This is obvious. So abelian is not a problem. And if you want to find out distributive property and other property of vector space, this is obvious. So you just check that W satisfies distributive property, distributive. So this is the important thing, that the inverse is also element of, or the negative vector is also element of the same space. Okay. With that, we can easily, so that concludes that actually the condition that something is a vector subspace is equivalent to saying that it has three properties. One is that the zero element of original vector is the element of this, and this is closed under addition and closed under scalar multiplication. Then it's called a vector subspace. Okay. And okay, so maybe we can give one or two more proofs. Maybe example. For example, diagonal. So if you choose a special kind of matrix, another example. So suppose this is your n cross n matrix. So n cross n of f. Okay. So this is n by n matrices, such that these EIJs are element of F. And here you can choose a special kind of matrix, diagonal matrix. Diagonal matrix means what? Diagonal matrix means that other than these entries, everything is 0. Okay. So only this can be non-zero or 0, no problem. But other than everything is 0. So what does that mean? That means so this is if A belongs to that diagonal set, so that means you write down this is Aij of this form, and Aij equal to 0 for all I not equal to 0. Whenever I not equal to 0, it is 0. This is diagonal matrix. And now we check this is a subspace of the original space. Original matrix is a vector space that I already proved that for any MN cross matrix will be a vector space, right? Now this is also a vector space. Why? Because see again the 0 condition 1, the 0 vectors is there, and that is nothing but the 0 matrix. Okay, so 0 matrix, 0 vector is nothing but 0, 0, 0, right? 0, 0, 0, 0. So everything is 0. And if we add to diagonal matrix, again it will be diagonal. To multiply by a scalar matrix, again this will be a diagonal matrix, right? So that is obvious that this is there. This is there, right? This is one example I just want to discuss. Okay. Now I will finish this by one nice property of subspaces, and this I can write down that whenever you take any intersection of subspace, that becomes again a subspace. So any intersection, it can be arbitrary also. Intersection of subspaces of a vector space, say V, is again a subspace. So this kind of theorem you already learned in group theory, that intersection of subgroups of group, right? And then similar thing is true here also. And the proof is simple. So we have a collection. So maybe let me write down this is the collection of all subspaces. Collection of all subspace of V, and you want to say that this element, that intersection of that subspaces. So let me write down that Vi. So these Vi's are subspaces of V. Subspaces Vi's are subspaces of some subspaces of V. So this is a collection inside this collection, and this is my new set W. I will show that this set is again a subspace, and this proof is also not difficult because each of the Vi's are having their subspaces, right? They have 0, and then 0 belongs to intersection, right? So the proof is what? So 0 belongs to Vi for all Vi is element of C. This implies 0 belongs to the intersection of Vi is element of C, which is nothing but W. So condition 1 satisfied. Condition 2 is also obvious. So it's closed under addition. What does that mean? That means we choose some V1 and V2 belongs to W. This implies what? That means V1 and V2 are element of the intersection, right? Vi belongs to this collection C. So what does that mean? That means it is each of those things. So these V1 and V2 are belongs to each of those things, right? So if it is belongs to each of those things, so it belongs to Vi for all Vi belongs to this, right? Now Vi is a subspace, and we know that if Vi is a subspace, then these additions are element of V1 plus V2 are also element of capital Vi, and that is for all capital Vi element of C, and done. So that means then this V1, small V1, V2 is element of the intersection of Vi, which is W. Similarly, same thing is true for number 3, that if you multiply by a constant, this element of W again. Okay. So if you take collection of all, if you take intersection of some collection of subspaces, it will be again a subspace. Okay. So with that, I'm going to finish first lecture. Okay. And we will learn some important other ideas called linear combination, other things in our next class. Okay. Thank you.